Welcome everybody. Today we're in chapter 8, section 1. We'll be identifying mathematical patterns in a sequence, and then we're going to use formulas to find the nth term of a sequence, which is simply a way of saying any term in a sequence. So n is for any term. What I want you to realize is that math is everywhere. So let's take a look at a little video where it's found in nature's different types of sequences. At the Fibonacci sequence. Creates a golden spiral as labeled by the ancient Romans. And that spiral is found all throughout nature. So pretty interesting, some of the places that these mathematical patterns end up in nature. The one that I mentioned during the video was the Fibonacci sequence, named after Leonardo Fibonacci, who was born in 1175. So, you know, even older than me, yeah, it's possible. But this golden spiral that comes from that ratio shows up in everything from artwork like the Mona Lisa. They have found that ratio to be part of the features of the art, to different types of shells or flowers in nature, hurricanes, the antlers on animals, even galaxies sometimes fit into that golden spiral. here's the Fibonacci sequence. So what's the pattern each time to get the next number? Right? That's what we're going to take a look at. Starts off 1, 1, 2, 3, 5, 8. What's the pattern? What do you do next to get that next number? Our first term is 1. Our second term is also 1. Third term is 2, so forth. How do you get the 1, 2, 3, 4, 5, 6, 7th term, 8th term, 9th term? One and 1 add up to 2. 1 and 2 add up to 3. 2 and 3 add up to 5. 3 and 5 make 8. 5 and 8 make 13. 8 and 13 make 21. 13 and 21 make 34. And it just continues that way. There's our Fibonacci sequence. Not only does it show up in nature, but it shows up also in the stock market. We'll see that in a minute. So, perfect time for a brain break. Why was Fibonacci afraid of 5? Why was Fibonacci afraid of 5? Because 5, 8, 13. Get it? There's your Fibonacci sequence. 5, 8, 13. Got it. This lady here is called the Fibonacci Queen. She works on Wall Street and she's able to, with pretty good accuracy, predict where stocks are headed. Are they headed higher? Are they headed lower? Are they going to stay about where they are? She uses Fibonacci levels. I don't necessarily claim to understand it, but she's using Fibonacci numbers to help figure things out.
Most every trader's heard about Fibonacci levels, but what's the best way to use them? We're talking with Carolyn Borodin today. So Carolyn, first of all, why does Fibonacci seem to work so well in terms of where stocks, ETFs and such seem to go to bounce off and come to as support, whatever it may be? Fibonacci just seems to be a level that works really well. Why is that?
Well, it seems to be a natural phenomena. I mean, there are some people that will tell you that it's just that a bunch of traders are looking at the same exact levels and it's a self-fulfilling prophecy. But I really don't believe that. I've actually taken this down to 1-minute charts and I've seen these patterns unfold over and over and over again.
Now, do you have a favorite level? Some people like the 618 or 127. Is there one that works particularly well?
I guess I would have to defer to the golden ratio or 0.618.
And why do you think that is?
Well, that comes with going through the whole number series and the fact that within the Fibonacci number series, the 0.618 ratio comes in between these numbers as you go out to infinity.
All right, and then I know a lot of people have trouble deciding where to draw the Fibonacci, which low to which high. How do you kind of get experience in knowing what's the best place to draw these lines?
Well, when I'm teaching people how to do it, I try to show them the key swing highs and lows. But if they don't get it, honestly, I just have to go over 50 or 60 different charts and keep showing them the lows and highs that I would choose and then see if they can replicate that.
All right, and then finally, do you look for confluence of Fibonacci levels on different time frames? So if a Fibonacci level of 618 is drawn on a 1 hour chart, and then on the daily chart, a similar level or another level kind of matches that area, does that make it a stronger trade of area of support or resistance?
I think that would make it a stronger area, but typically what I'm doing is a confluence of levels on each time frame. So I may have a confluence of levels on a daily chart, but I'm also going to look for a confluence of levels on a 15-minute chart. And sometimes they will match up, and that will strengthen the trade.
Would you put more size on because of that, or just be more likely to take the trade?
I think it might be a little bit more aggressive.
Carolyn, thanks for your time.
Thanks for having me.
You're watching the MoneyShow.com video network.
1 cheesy tortilla chip, 1 cheesy tortilla chip, 2 cheesy tortilla chips, 3, 5, 8. Hey, math geeks shouldn't be allowed anywhere near certain foods. What's wrong with Fibonaccios? There are only 12 left. Now what? Hut 0, Hut 1, Hut 1, Hut 2, Hut 3, Hut 5, Hut 8, Hut 13. Is it the Fibonacci series? Correct. Touchdown, Marcus. Woohoo! We're sick of football favoring the brawny. Hut 3, Hut 0, 2, 3, 2, 5. There's a series. There's a pattern there. So in your notes, jot down what a sequence is. It's an ordered list of numbers. Could be anything as simple as 2, 4, 6, 8, and we wonder what comes next. No, it's not. Who do we appreciate? What's the first term? What's the 10th term? And then what would be the correct formula if I gave you a list of formulas? Let's take a look at how to figure that out. Our first term would be 2. Our 10th term, well, we could either keep writing them out till we hit the 10th term, and that's not bad if there's only 10 terms. But if there would be, say, 100 terms or 1,000 terms, I certainly wouldn't want to write that out. I would want to have the formula, where n is telling you which term you're looking at. So in these formulas, n squared plus 1, or n plus 1, 2n, 3n squared minus 1, n represents which term? Is it term 1, term 2, term 3, term 4, or in our case it would be term 10. So if we can figure out the correct formula, we could find that 10th term very easily by plugging in a 10 for n. How much is our sequence changing by? All right, so we're adding 2 each time. We have a common number that we're adding each time. We'll call that the common difference. 4 minus 2, 6 minus 4, 8 minus 6. There's a common difference there. So we could just continue it on. Let's go ahead and do that. 2, 4, 6, 8, 10, 12, 14, 16, 8. I can write it. 18, 20, 22, and it could continue on forever. That's why we have those 3 dots. So we want the 10th term. Term 1, 2, 3, 4, 5, 6, 7, 8. Who do we appreciate? 9 and 10. There it is. 20 is our 10th term. So, how do we get to that using these formulas, right? Our formula has to work for each term. If you try 3 separate terms and your formula works, it's most likely going to work for any term. But you can't just assume that because it works for one term, it will work for every term. Try 3 different terms, you'll be good to go. So, which formula are you guys thinking of trying? Okay, let's just do the first one. N is 1. N is 2. N is 3. If I plug in 1, 2, and 3, I should get back 2, 4, and 6 from my formula. 1 squared plus 1, hey, that's 2. It must be this formula, right? Well, remember, I said you can't just try it for one term. You have to try it for at least 3 terms, and then you know you're good. Because this formula here, 1 plus 1, is also 2. This formula here, 2 times 1, is also 2. This formula here, 3 times 1 squared minus 1, 3 minus 1, is also 2. So just plugging one term in doesn't get you the right formula necessarily. Let's try a second term. Plugging in 2 for n. 2 squared plus 1. Well, it's not that one. I needed a 4. I got a 5. 2 plus 1. Not that one. 2 times 2. Maybe this one, right? We've only tried 2 terms so far. 3 times 2 squared minus 1. 3 times 4 is 12. Minus 1 would be 11. Not this one. I'm going C. And if you plugged in your next term, 2 times 3 would indeed give you 6. 2 times 10 would get you straight to your 20. This is an example of an arithmetic sequence. You are adding, or sometimes you're subtracting, that same number over and over again. This is a different type of sequence. We have 1, -1, 1, -1, 1. What's our first term? First term would be 1. Third term, 1, 2, 3, would be 1. 99th term, 100th term, oh my goodness. And we don't even have a formula, right? But there's a pattern. N equals 1. N equals 3. N equals 5. N equals 2. N equals 4. So what do you notice? When your terms are odd, you get 1, 1, 1. So the 99th term should be equal to 1. When your terms are even, 2, 4, 6, the next one's going to be equal to -1. Then we get -1. I'd ask if there was any questions, but you know, you guys are kind of quiet today. All right, you try. What are the first 5 terms of a sub n? That's how you read that little n notation. It's down in the basement, just like when we did logarithms. We had that number down below. This is called subnotation. A sub n equals n squared plus 1, and then we will graph it. Let's figure out your first 5 terms. You just say a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. And we plug in 1, 2, 3, 4, 5 in place of our n. So 1 squared plus 1, 2 squared plus 1, and so on. Why don't you pause your video for a second and figure those out. We'll compare notes. All right, welcome back. 1 plus 1 is 2. 4 plus 1 would be 5. 9 plus 1 would be 10. 16 plus 1 would be 17. 25 plus 1 would be 26. Those are our first 5 terms. Well, how do you graph it then? Well, n is 1. N is just like having an x. This would be your y. You could think of this as y equals x squared plus 1. The n would be your x, and then your answer would be your y. So we have 1, 2. We have 2, 5. And then that's really all that fits, right? Well, let's just graph other things too. We could plug in 0. 0 squared plus 1 would be 1. We could plug in -1. -1 squared. Remember, in parentheses, -1 squared, -1 times -1 is 1, plus 1 would be 2. -2 squared, well, that'd be 4, plus 1 would be 5. Guess what? We have a parabola. Hopefully you recognize that. You had an n squared. That's a parabola. Right? Let's take a look at another type of sequence. This one was noticed by Johann Carl Friedrich Gauss back in the 1700s. He was born April 30th, 1777. Lived up until February 23rd, 1855. He was a very smart mathematician. He's got a lot of areas that he contributed to, not just mathematically, but elsewhere too, including all the way up to astronomy, optics. He had a very large part in figuring out the orbits of planets. So, at 8 years old, Gauss was sitting in 3rd grade, and his teacher thought he would have a really easy day. He thought he would give the students a hard problem, and it would take them a long time to do. After a very short time, Gauss came up with the answer, and his teacher immediately accused him of cheating. He was asked to add the numbers 1 to 100. So that's 1 plus 2 plus 3 plus 4 plus 5, all the way up to 98 plus 99 plus 100. So here's what he was asked to do. And I'm not going to write out all the numbers, so I'll say they continue on. And then I'll just pick it up here, maybe around 98 plus 99 plus 100. Now, back in the 1700s, they didn't have calculators. They certainly didn't have Siri or Google to help them figure it out. No AI. So what did he do to figure it out? Well, he noticed a pattern. Look at the first number and the last number. Look at these two numbers. Look at these two. What kind of pattern can you notice with those? You need to pause for a minute. Go ahead. Here's what he noticed. If you take 1 plus 100, you get 101. If you take 2 plus 99, you get 101. I think I see where this is going. 3 plus 98 is 101. So he realized that there's going to be pairs of numbers that add up to 101. If he could figure out how many pairs, he could multiply by 101, and he would come up with his answer. So, how many pairs? Well, if you have 100 numbers and you're using 2 of them, that means you would have 50 pairs. So, very quickly, can you go ahead and multiply 50 times 101, and you will have the sum of all those numbers from 1 to 100. Gauss went up to his teacher. Teacher said, "Cheater, cheater, pumpkin eater." Okay, maybe he didn't really say that, but the point is, he was accused of cheating. Gauss just figured it out, that's all. He was smart. So, let's add 1 to 10 using his little pattern. 1 plus 2 plus 3 plus ... plus 10. Well, 1 and 10 add up to 11. 2 and 9 would add up to 11. So it looks like we're going to have 11s, right? You have 10 numbers. How many pairs do you get? 5. 5 pairs times 11. Our total would be 55. Pretty cool stuff, huh? Mm-hmm. Not bad for somebody in 3rd grade, 8 years old. So, let's create an explicit formula that describes the nth term of a sequence like what Gauss used. Our formula will help us find the total of the sum of whatever number of numbers we want. 1 plus 2 plus 3 plus, I don't know. How high do you want to go? 10, 100, a million? Doesn't matter. To do that, we kind of need to look at a little bit more of this. So it's 1 plus 2 plus 3 plus n. If this is my 100th term, the number before that is 1 less, so it would be 99. So if this is n, then this term is n minus 1. And I'm going to put that in parentheses just so that we know that's a single term. So we have 100. We have 100 minus 1. We have 100 minus 2 to get you to 98. So the term before this would be n minus 2. Using Gauss's little formula, we'll take the first one plus the last one. Well, 1 plus n We'll call that n plus 1. We usually put the variables first when we're adding those things. It's in standard form that way. Next up, we need 2 plus n minus 1. If you need to, come off to the side. 2 plus n minus 1. Combine like terms. I get m plus 1 again. For each of these pairs, 3 plus n minus 2 is going to be n plus 1. So to make our formula, what we need is our n plus 1, and we multiply that by the number of pairs. How many pairs do we have? Well, let's think about it. When we had 10 numbers, we only had 5 pairs. When we had 100 numbers, we had 50 pairs. When we have n numbers, how many pairs would you get? You have n divided by 2. You'd have half as many. So our explicit formula, our sum of all these numbers would equal n divided by 2 times n plus 1. That's our formula. Number of pairs times the sum of that first and that last one. So, without a calculator, why don't you add up the first 20 numbers? You have 1 minute. Go. How many pairs? 20 numbers. I would have 20 divided by 2. I'd have 10 pairs. How do I multiply by 10? Without a calculator, I simply take my 21 and I add a 0. There we go. Done. Homework is chapter 8.1 on patterns. Have a good day, guys. See you next class.